Okay, to our first talk of the third day. It's unlocking hardware security, red team, blue team, and Trojan tails. Our speakers will present a case study on a red team versus blue team approach to protect hardware against Trojan horses. And our speakers, trying to get the order correct, Steffen Becker, then René Valendi, and E7P. They are all affiliated with the Max Planck Institute for Security and Privacy, as well as the Rhein-Ruhr-University Bochum. Please welcome them with a huge round of applause.
All right, thank you very much for the warm welcome and for the kind introduction. Yeah, it's great to see so many of you here early in the morning. Our talk, Red Team, Blue Team, and Trojan Tails, evolves around an academic paper which was this year published at IEEE S&P. And it deals with the detection of a certain kind of hardware Trojan in chips which are manufactured in modern CMOS technologies. This research was, of course, a team effort, so of course with E7P and René, but also kudos go to Torben, Christian, Amir, and Christoph, who were part of the project. So, to give you a rough idea of what to expect today, I show you this slide. So our talk is split into three parts. First, I will try to lay ground and provide some background information on hardware Trojans. Then second, E7P will present our red team versus blue team study and the results. And then last, René will talk about some of our ideas regarding human-centered reverse engineering. So let me start with a bit of background. These days, even trillions of digital ICs are deployed in a multitude of systems and devices. And on the one hand, they are in everyday devices like smartphones, laptops, or cars. Yeah, but they are also deployed in critical infrastructure, such as energy or telecommunication grids or power plants. And due to the superior performance for many tasks, those application-specific integrated circuits fulfill many mission-critical objectives. Yeah, and I've listed some of those here. They directly implement cryptographic algorithms and encrypt. They do location services. They implement wireless communication, real-time monitoring, and so on. To give you a feeling for those tiny and complex devices, let me show you this short video here. So it starts zooming into an opened IC, which was etched with a digital camera. Yeah, and at this point we can only anticipate the many tiny structures here. Yeah, we don't see much. And then as a resolution of roughly 1 millimeter, it switches to the scanning electron microscope. And here we already see the metal structures forming interconnections. And as we go deeper and deeper, we can imagine we have three-dimensional structures. Yeah, and then the width of one of those metal tracks was 1 micron here, so 1,000 nanometers. And modern transistors these days are below 20 nanometers. So in the width of one of those metal tracks, you can implement more than 50 or even 100 transistors these days. So to just give you a feeling. And in our experiments, which we will show later, we went down to 28 nanometer transistors. So the production of such highly complex microchips requires many process steps. And now, of course, I cannot cover all of this in this talk, so I will give a very simplified version of the IC design flow and of the globally distributed supply chain. So the design flow starts with a high-level design on the left side, where hardware is implemented, usually with hardware description languages. Yeah, then next comes the synthesis, where this hardware description languages is transferred to a logic of, say, Boolean gates. Next comes the physical layout, the mapping to the physical resources, and then, of course, during all those steps, but especially at this step, we have extensive verification, so that we can actually kind of make sure that the design which goes into fabrication will work in the end. We can still not make sure 100%, but we can do our best to verify this. Then comes the actual verification of the IC on wafers in highly specialized facilities. And then the silicon dies which come out of those wafers are packaged, and maybe those packaged dies are assembled on a PCB. So this is, again, distributed across a globalized supply chain. We have many, many designers of intellectual property, but we have only very few design synthesis or place and route tools, and many of those are even proprietary. Yeah? And then the IC fabrication is mostly outsourced. There are only very few who maintain their own capabilities. And also the packaging and PCB assembly is usually outsourced. So looking at this distributed design flow is crucial for realistic threat assessment through active attackers. Yeah? And so now coming back to our mission critical objectives which the chips fulfill, we can see some of the supply chain threats by active attackers as a weakening of cryptographic primitives, information leakage, denial of service, or even safety hazards. And the rule of thumb here is like the lower the level of abstraction, so the further we go to fabrication, the harder it becomes to meaningfully tamper with a design, but also to detect malicious manipulations. Yeah? So now let's take a closer look at what an active attacker can do in this distributed supply chain. So first, a malicious designer might interfere with a circuit already at the IC design level. So we've seen this, for example, with deliberately weakened cryptographic algorithms by nation-state actors. And we also see this in, say, export regulations. Yeah? Another threat is the implementation of malicious third-party intellectual property that may compromise my whole IC. So progressing through the design flow, there also may be manipulated design tools, yeah, either ex-factory, or they could also be modified through malware. And such tools may automatically insert manipulations during the synthesis or layout steps, and even tamper with the verification tools to prevent detection. So now for a moment, let's jump to the end of the design flow, to the PCB assembly. Here it might be possible that an attacker adds spy ICs to the PCB, or even manipulates the routing on the printed circuit board. And this could happen either during the assembly or during transportation through shipping interdiction. That's what the three-letter agencies like to do, like on those photos from the Snowden files. So in theory, those manipulations may well be detected through several means, for example, optical inspection or product teardown. There's a big story about such a system-level hardware Trojan, how we coined it, which caught considerable attention in the media. So it was published by Bloomberg, called The Big Hack. It's based on anonymous sources. And this hardware Trojan, which was presumably found, it consisted of an additional chip placed on Supermicro server blades next to the baseboard management controller, BMC. And this BMC includes an interface for remote control. So those allegedly Trojanized boards were used by some of the important players here, Apple, Amazon, for tasks such as video compression or drone operations, or secure video conferences. So it was definitely a high-impact target for hardware Trojans. So while all those players, Amazon, Apple, and co., they denied the attack, the article still caused a lot of media attention and sparked political discussions, and maybe even some decisions with respect to the recent EU and US CHIPS Acts. But the technical details, they remained largely unknown, at least to the public. public. So this is why I would like to refer to this talk, which was given by Tremel Hudson at 35C3, and where all the technical details were actually covered. And he concluded that such an implant to the BMC, to the baseboard management controller, is indeed feasible. However, hiding the implant, that is not an easy task. Yeah. So now let's switch to the main focus of our talk here, of our work, silicon-level hardware Trojans. So those on-chip manipulations, they go directly to the silicon and can enable arbitrary manipulations and are arguably really, really hard to detect. They may consist, for example, of added or modified logic cells, or even routing manipulations or manipulations to the dopings of the transistors. And they could be inserted just before fabrication, yeah, by a so-called malicious fab, to the already placed and routed design files, or even after fabrication through edits, say with a focused ion beam. So to get a grasp of this, let's make a basic example with this simple circuit here for debugger authentication. Yeah? Only if both signature valid and data ready here are true, the debug interface will be enabled. Yeah? Now consider an attacker who changes this AND gate to an OR gate, and we can see that this way it is enough to only have one of the values true, say the data ready value, and we can bypass the debugger authentication. Yeah? So this is a minimal example of such a silicon level hardware Trojan. So now let's take a look at the actual threat model. So how does it look like? And how would one go about detecting such a Trojan? So remember those fabless design house here on the left? Yeah, this would prepare the design and send the finished placed and routed and Trojan-free, so we don't have a malicious designer here, Trojan-free design to the external fab, which is malicious in this case. Yeah? Now the malicious fab inserts the Trojan to the silicon and produces the chips. And then there's also a detection lab, which receives both the original design from the design house and the Trojanized chips. And it needs now to detect the manipulations. And this is usually done by imaging the chips and comparing design and images. So to get a feeling how this works, here we see a cross-section of a chip. And for imaging, it's important to know about the general buildup of this chip. So on the lowest layers, there's the transistor level, and this is where all the logic cells are placed. Yeah? And we're looking for manipulations of logic cells. And above, on all those layers, are the interconnections between the cells, and they are realized with 3D routed tracks. And as a detection lab, again, is interested in finding modifications at the cell level, we have to put the chip under a microscope upside down, so to image it from the backside, as symbolized here. So for this, I have to say that this is a destructive method, and that the chip won't work anymore, and you might need even more than one chip before you figured out the correct recipe, because you need to thin it from the backside before you can take the pictures. So here is an exemplary scanning electron microscope image taken from the backside, from the bottom. The horizontal lines, which you can see in both those images, are power and ground, and then the dots between those lines are vias. And those vias connect to other layers. Yeah? And one observation which we can make here is that standard cells with the same functionality have the same via pattern. And those with other functionality can be distinguished. Yeah? So if we make here the example of our simple Trojan and put this under an electron microscope, this is how it might differ from the original implementation. Yeah? You can see the differences in the via positions here. And then remember, we operate here on very tiny devices, which potentially have many, many, many standard cells. So I just want to give one more quick reference, because I only superficially covered some of the IC design and manufacturing basics here, the ones needed for this talk. I would like to refer you to this talk. So if you would like to know more about how chips are made, I highly recommend this 34C3 talk by Ari. With this, I would like to hand over to E7P, who will present the details of our hardware detection case study.
Yeah, hello. So I'm presenting the technical aspects and also our proposed algorithms that we want to show you for the comparison between design and chip. So as we just learned, hardware Trojans, that are some broad term, both from the attack perspective as well as the actual modifications. And our goal is to find even smallest ones, just requiring changes in a few, or even maybe one single transistor or maybe a logic gate in the design. And even such small modifications could lead to undesired behavior, as we have seen. And on the bottom of the slide, there you can see again here an additional standard cell on the top, and on the bottom again this replaced cell. So now how should an attacker be enabled to fiddle around with the cell layout? Well, until a chip is produced, many steps, often outsourced to companies all over the world, have to be taken. And due to this distributed manufacturing, you can't control every single step maybe, or maybe an attacker gets in the hand of the design file and can modify it in between when it's sent to the fabric. So our main research question is now, how efficiently can we detect such a hardware Trojan in full-sized ICs in modern CMOS technologies? Yeah. So how do we do that? We somehow adapt this analysis a bit to our needs, as we have some chips already produced. So now we actually modify the design file instead of the chips before sending them to the fabric, because in the end the detection lab here on the right, it's just important that the design file and the actual chip images or the actual physical samples differ and have this difference, and we can emulate that by simply editing the design file. So we have here this strictly split setup, and we have a red team that actually makes this malicious modification, and we have the blue team that is our analysis lab that wants to find these. And how that works in practice, I will show later. So now let's get started with the red team and how the malicious modifications were introduced in the integrated circuits. First of all, here we can already see the 4 different ICs that we had at hand. They were part of different research projects, and thus were developed beforehand. So we could simply take these chips and then progress with them. As you can see, these are in different technology sizes, ranging from 90 nanometer, over 65 nanometer, and 40 nanometer, down to as small as 28 nanometer technology sizes. And the dimensions of these chips are roughly 2 by 2 millimeters. So these are quite small already, but they contain a lot of standard cell-based logic, which is great for us when we want to find logic-based hardware Trojans. So how does this emulation now works in detail? Coming back to these different pictures, here what we want to reach is that the original chip at some spots does not have some standard cells that the Trojanized chip would have. So we turned basically around our progress here by removing selected logic cells So the original chip would not have these, but the design file has the added logic cells, right? And for the replaced logic cells, nothing would change really, because it doesn't matter if we replace a NOR with an AND or vice versa for our detection methods. And yeah, in total, the red team introduced 10 modifications per chip. So we have 40 modifications in total. That's 6 added logic cells per chip and 4 replaced logic cells per chip. And in total, we have over 3.4 million of standard cells. So we just modified a fraction of a percent. So now I'm coming to the blue team and how we progressed with the chips. The blue team receives the physical samples as well as the design file by the red team. So now the blue team's part is to somehow prove that there is some difference and where exactly these differences are and in which cell position. So the physical samples need to somehow be imaged with a microscope and then processed by some algorithm that then could compare the design file on the one hand with the actual images from the microscope. For imaging, again, it's important we are looking from the down as we are interested in the standard cell layer. So what do we do now? So we flip over the chip, then mill down the silicon substrate layer down to a very thin, then etch away even some more silicon with a choline hydroxide etching process, and then actually scanning the whole standard cell layer with a scanning electron microscope. Noteworthy to say is that this last step is very costly, both in time and effort. So, and the machines are, you can't afford them, basically, yeah? Multiple millions of dollars. But in the end, we can get these silicon die shots of the standard cell layer. And here on the down, you can actually see the images we now received from the microscope. And in the orange rectangles, there are the interested areas. And on the top, for comparison, there is again the design files. The total file size of these tiled images, they are tiled in a mosaic because they are so large, is around 300 gigabytes uncompressed grayscale images. And the actual resolution is down to 4.8 nanometers per pixel. So that's very huge, and manually, I would say, you cannot handle them. So when zooming into these pictures, you can clearly see how different the different technologies look like, but all of them have in common that each standard cell is standing out by these bright white spots, that is the wires that connect to the routing layers above. And if you zoom in even more, you can really see every single standard cell and can feed them to the algorithm later. So, and with that, I continue to present you the actual analysis algorithms that can detect manipulations. So for that, we have a small roadmap. First of all, we need somehow all the coordinates in the same format, or maybe overlay them somehow, so we have a good assignment between the design file positions and where they are in the actual microscope images. For that, we might need to somehow transform the image or to scale them or something. So in the end, we have a perfectly overlaid design file to the chip. And then in the third step, we apply our algorithms to every single cut out standard cell, and then can compare them or do further stuff. Yeah, for the first part, the design file, they are in the standard GDS2 format. And luckily, there's an open source library called GDSPy for Python. And with that, it's very simple to just extract all the coordinates of the bounding boxes of each standard cell. And in the next step, we take each of the tile positions of the stitched mosaic image of the whole chip. And we also import these into our Python script. Then we need to find out about the correct rotation or flipping maybe, and to be able to actually overlay a design file with the chip images. And for that, we start with a simple, 4 edges. So where are the 4 edges in the image? And then we try to overlay the GDS2 file over this. And we already see how the rotation and flipping might need to be. But then there's still some offset in the alignment. And to correct this, we again take the 4 edges of our chip and do a perspective transformation that is then able to make it more precise where the actual standard cells are. So now we can basically cut out every single cell and also every single area where no cell should be, or no standard cell. And now we can start with processing them in our algorithms. So now we have 2 categories of algorithms. One is that we want to detect if there are additional cells that are not planned due to the design file. And the second case would be replaced cells. Yeah? So we need kind of some different algorithms for each other, and I present both of them. So the first one is the wire detector, which detects bright white spots inside the standard cell. And if there are bright white spots, then we are perfectly certain that we have an additional cell that is not in the design file. For that, we use classical image processing techniques with OpenCV and to get reproducible results. And we basically binary threshold the image, then verify that the contrast is high enough, and in the end also apply some template matching with a ball-shaped gradient. And this, on the right top side, you can see works quite well, even with some distorted or low-quality images. But on the other hand, which we absolutely don't want, is that these false positives that could be detected where no bright white spot is or wire. Yeah. But these false positives are very few, as we can see in the results later. Finding replacements is a bit different, as now we might more or less compare multiple standard cells against each other. And for that, we iterate through all of the standard cells. And the first occurrence of a unique label of the standard cell is taken as a golden model or template for all further cells of the same label. And now the template matching algorithm is applied to other occurrences with the same label. So we expect that a cell that is labeled the same also looks very similar or maybe equally. Yeah. And so we have 3 pictures now. The first one is the first occurrence that is taken as a golden model. Then the second one, the second occurrence, our algorithm would tell, well, the images are equal, so we don't have any manipulation here. And the third one looks quite different, so our algorithm would say that is a modification. But not everything is perfect. This simple template matching algorithm leads to too many false positives when the threshold is too low to say if it's a modification or not. So we need some additional measure. And for that, again, we take our wire detector, which we used for these additional cells. But now we use it to generate artificial wire masks and apply the template matching with between these wire masks instead, so we can get more precise results here. And now I have some live demonstration of our algorithms, if the VOC can switch over, yeah. So I just start this run script, and this first loads the GDS file, and then iterates over each of the tile images, which I have fed into the algorithm. And now the wire detector is going over every single standard cell detected in every tile image. And after some tiles, there will be a match, or basically a mismatch, as we can see here. And so this is the whole tile image, and the orange borders are empty space cells, as well as the blue borders that depict standard cells. And when zooming in here on the bottom, this is actually an orange border cell, so it should contain nothing, but here there are some wires, so this is a detected manipulation. Now the algorithm switches over to the replaced cell detection, because for this live demonstration. And as you can see, it takes a bit more longer to analyze for cell replacements. This is just because of the template matching algorithms. But also after some tiles, we have another tile here, where here on the top, there's a cell detected which should look like the one below here, but instead looks different. So also detected here. And in the end, after the whole iteration of all tiles, some reports are generated where are some details of the algorithms, like here the cell replacement, here is the cutout cell, and here's the golden reference model. So this is a true positive, right? And we have the same and some debug information as well for the wire detector in additional cells. So now we can switch back to the slides, please. So now I'm coming to the results. How did our detection algorithms perform? Let's review some chip statistics. So all 4 chips contain between hundreds of thousands up to 1.5 million cells each. And they have areas between 1 square millimeter and 2 square millimeters. And yeah, so now coming to our results, they show that our simple algorithms perform very well here. And especially for the additional cells, we have no missed cell, so we could detect all of them. And by that, we also have very few false positives in the additional cell detection. While the replaced cells were also all detected for 90 nanometer, 65 nanometer, and 40 nanometer, we still have 3 undetected cells in the 28 nanometer chip. And we will see in a few slides why that is. So, yeah, and also we have some more false positives here. And while the scanning electron microscope takes 1 to 2 days for recording these chips, the detection algorithms all run, like between 2 and 5 hours. So that's quite fast compared. Yeah. Here are some selected true positives in the cell replacement detection. And as you can see, they are really true positives. They are differing between the top row and the bottom row. And some of the false positives are shown here. And most of them are caused by debris or dust that settle down on the chip and thus covering the standard cells we want to analyze. So this will be detected as a replacement, but as you can see, nobody knows from the image if the cell below is actually a replacement or not. This debris happens when during the preparation steps, when some parts or particles of the silicon that is removed maybe settles down there, and even polishing does not remove all of them. Here's one of the false negatives instead. So this is one we could not find with the algorithm. And on the left side, you can see the two images, and they are very, very similar, but maybe you can spot that on the top of these, there's minimal differences. So we could improve. Maybe it is possible with a better scanning electron microscope to record this 28 nanometer chip. Or we can maybe machine learning based algorithms could be developed that can deal with such low quality images, leading to cheaper imaging. So what are the takeaways? So Trojans that are easier to implement, maybe by taking not existing cells, but adding additional cells to the chip, that are also easier to detect. And whereas the replaced cells are a bit more unobtrusive and harder to detect with shrinking technology sizes. The detection can likely be improved by advanced detection algorithms and SEM images, better images. And if the quality is high enough, we can detect these modifications very well. One last point I would note is that we released all of the 300 gigabytes of image data as well as design files on and linked to them on our GitHub repository, where you can also find all the algorithms implementations. So. And now I would like to hand over to René, who will tell us something about human aspects of reverse engineering.
All right, thanks so much, E7P. So, you now all go to our website, you download the algorithms, and I don't have any mic, apparently. Hello, check, check. Okay. So, thanks so much, E7P. Now into the human perspective. So we now all just go to the website and we grab all the algorithms, we run them, and help our security is a solved problem, no? Well, it's not that easy. I recall that I promised in our abstract that I'd talk a bit about how our blue team worked, and it will then become very clear pretty soon that automate all the things is really nice in theory, but it doesn't work that well in practice. We'll have some ideas how we can tackle that complexity and also have a couple of ideas how you can help with that. So perhaps the most prominent issue that we found while working with those algorithms is that we ended up with a ton of different parameters that we need to fine-tune to be able to use our algorithms efficiently. And this is required to some extent because we need to match those parameters to our input data. And I have some examples here. So those are 4 styles. You've probably seen those before in the E7P slides from the 4 different chips. And you can very clearly see, if I have a pointer here, that the image quality is very different in terms of contrast, sharpness, brightness. And this, of course, affects all the thresholds in the algorithms. And those thresholds control what the algorithm considers a positive in the sense of manipulation. Yeah, so this leads to this kind of setup where all the different algorithms have different parameters, and then for each of the different chips, the blue team had to sit down and iteratively tune those parameters in order to dial in those algorithms to work well. And in the end, those parameters control the detection sensitivity. So what amount of deviation from our golden sample do we consider normal? And what do we consider a manipulation? Asked differently, well, if your analysis process doesn't find any manipulation, is that because your chip was not manipulated? Is it clean? Or are your parameters just too lax? And then on the other hand, choose your thresholds too tightly, and you produce thousands of false positives, and then that's really tedious to manually check. And so you can think of this somewhat as like an ignorant paranoid dial on those algorithms. And getting that dial tuned just right is a real challenge. So let's assume for a second that you've done all of this, you've tuned all of your parameters well, but unfortunately we still have some challenges ahead of us. So here are 2 really nice logic cells, super crisp, clean images from one of our chips, and we've looked at the design files and we're pretty sure that those are the right ones. And now, in another place on the chip, you see this. Are those the same cells and the image quality is just really bad? Or is this a sampling artifact? Who knows? And I think the point I'm trying to get across here is that, well, automation is nice, and we certainly need it to tackle the vast amount of data that we have. There's like 300 gigabytes of data. But it has limits. And for a good result, you will always need an experienced analyst to work with those algorithms, to tune them properly, and to interpret the results. So, how do we get there? And to figure out whether we actually have a manipulation on our chip or whether it's just a sampling artifact, it kind of helps to put yourself in the perspective of the adversary. So what would this manipulation cause here? Was this a manipulation that appears to be of some use to the attacker? In that case, it's pretty likely that you actually found a true positive. Or is it just garbage? So let's look at this example here. Let's look at this black area in the top left here where there's nothing before. And let's now assume that we image our chip and we find, whoops, there's a few dots in there. So there's a cell now. And let's assume for a second that this cell is an inverter. Yeah, so there's this one wire, and you connect an inverter that has chip enable as an input and chip enable as an output. Well, that doesn't make too much sense, does it? So what would happen here is, well, you cause a short circuit. The chip would immediately halt and catch fire the moment you try to turn it on. That would be somewhat obvious to the end user. It's not really a good manipulation, is it? So it's pretty likely that this is just a sampling artifact. There's like some speck of dust on there, and it's not really a manipulation. Going back to the example that we had before, that Stefan brought up, if we look at this area and we assume that we've replaced this AND with an OR cell, and looking at the signals, we now have a debug authentication bypass. That's pretty likely to be actually a manipulation because it's really helpful for the attacker. Of course, this is just an example. Good testing should, well, maybe, catch this. But more sophisticated instances that are a lot harder to track and that require some amount of triggers can be built in the same way. So this all sounds like a pretty straightforward process. Now you look at the circuit diagram and wait, circuit diagram? Well, how do we even get from the left side to the right? Well, we're obviously missing a couple steps, so we still need to figure out what logic gates each of those little wires and black areas really are, and we need to know how they're connected so we can actually draw the circuit diagram and make this educated guess. And that means we need to get a bit into netlist reverse engineering. So I only touched on this really briefly here. There's a couple of great talks out there that you should really watch if you're interested in this. But the essence is you need to go from the left side of like, I need to put the chip under the microscope, to the right side of understanding the data flow and all the logic functions that are implemented on the chip. And bonus points if we can do this in a machine-readable way, because, well, automation is nice. So we've actually dabbled in all of those things. If you want to learn more about this, hit us up after the talk. We can chat about this. The brief overview here is well, those are the first couple steps that we've shown in the case study already. So you take the chip, you image it, you detect the various cells on it. This is all something we know. And then we need to recover the netlist. So we need to recover the abstract description of the circuit diagram. And if we recall, the stack of the chip here means we need to image all of those layers potentially, as long as we don't have the design file. So it's quite tedious to actually do that, but it is possible. And then we end up with some kind of netlist, which, well, in practice, looks a bit more like this, and that's like a really tiny excerpt of a really tiny module of a really tiny chip. So you can get like hundreds, thousands, millions of gates, which means that to make any real sense of it, you need to partition the netlist. You need to recover this high-level information of what is this functional block here, like which gates do, well, the debugger authentication, for example. And then in the end, if you do this properly, you end up with this kind of diagram here, where you have all of the different input and output signals of the different blocks that realize specific functions on that chip. If you want to get into the details here, there's a great talk by Carsten Nohl and by Starbuck back from 2008. It's called Chip Reverse Engineering. It's a pretty nice one. So if you look at this talk, for example, you see that tools can support reverse engineering. Many of those tools are closed source. Many of those closed source ones are exorbitantly expensive. But there are some open source alternatives. I just mentioned briefly is this MIST, this is a stitching tool that's used to align all of the microscopy images. We use this in our case study as well. And then there's a tool called dgate. This is a tool you can use for this, okay, which cell is this thing here? And then in the end, there's a tool that our group also developed. It's called HAL, the hardware analyzer. It's also on GitHub, which is a tool that we can use to do this netlist partitioning, and then you can also script the interpretation of that netlist to some extent. But I'd like to offer a different perspective here. Yes, tools support hardware reverse engineering, but it's driven by humans. Now, every single step in this flow here requires humans. There are skilled machine operators that do the imaging, and there's people who write code to do the parameter tuning and custom tool development. And then also there's a lot of sense making and ingenuity and intuition that goes into this netlist partitioning and sense making stage, and to make a sensible decision on what does this manipulation do. Yeah? This has, in the recent years, led us to start some interdisciplinary work in this space, and we work with some psychologists with a focus on cognitive science in order to actually understand how hardware reverse engineers work and how we can support them better. So to put this thing a little more formally, this is some older work we did where we defined that HRE success mostly depends on, yes, manual and tool-supported analysis, but to a large extent it depends on the cognitive processes of problem solving which steer this analysis without going too much into the psychological details here. There's been really little research on the latter, and so the strategies are pretty poorly understood. But we believe that if we understand those human aspects and those cognitive limitations that people naturally just have a bit better, we can help make hardware security testing more accessible. We can do it more intuitive, more usable tooling, and we can also work on training that tackles those problems more precisely. Some practical applications for what we can do here. I talked earlier about automate all the things is probably not the solution. I would argue that hardware reverse engineering is inherently a human-computer interaction problem. So the focus should probably not be on just automate all the things, but maybe the focus can be on automate repetitive tasks where that makes sense. Yeah? So the number crunching, the pattern recognition, maybe throw some ML in there if you want to. And then spend the rest of your development time to support reverse engineers in their cognitive processes by tools and by accessible documentation. So, summing up, there is what I suggest are 3 pillars to making hardware security and hardware security research and testing more accessible. One is we need capable and open algorithms that are suitable to be applied to real-world data and devices, not just toy examples. And chipsuit and HAL are some examples we provide here. You can look at the slides later. We have the QR codes if you want to download the stuff. Highly suggest you check it out. We're still looking for 3 Trojans. Help is much appreciated. Then it's accessible and intuitive tools, and that means at different levels of experience. That does not just mean have tools that work really well for the people that have been working with them for 10 years. It means have tools that you can adapt to people who start out in this field to get into it without being immediately overwhelmed. And it also means we need training resources, which, as this is a traditionally quite closed community, this hardware security field, or hardware design field, outside of enterprise settings. And this latter part is some research we just recently started. We're running a hardware reverse engineering course at a university, and we're trying to look at how this course performs and come up with some actual guidelines. So how can we teach people to do hardware reverse engineering efficiently? So this is interdisciplinary research we're working on. Especially this interdisciplinary research, I think, has a huge potential in this field. Yeah, we've talked a lot about algorithms. We've talked a lot about like making things more efficient and taking the latest scanning electron microscope and throwing it at the data. I think it's not enough. We need to collaborate with other fields because humans drive hardware reverse engineering, not algorithms. So, before I sum up, I need your help. And we want you to play some games for science. So what I've brought with us here is a tiny hardware reverse engineering game. If you've ever seen a circuit diagram, you can totally play this. Yes, there's multiple difficulty levels. I will release this to the public now and hope we don't immediately be slashed.it. I really recommend you check this out on like a big screen device. Big tablet, laptop, whatever, but you can still grab the link here. We'll probably later be around at Labor at Chaos West. You can talk with us there, and we probably also have some laptop if you want to play it there. We use this game to assess cognitive factors of reverse engineering. This is our new beta of this game. We're launching a study starting next year, and I'd be super happy if you could help us beta test this and find as many bugs as we can. So. Final slide. So hardware Trojans can be really subtle. They can maliciously alter behavior of the circuit and are really hard to find. Complex supply chains just make this inherent. Our red team versus blue team approach and algorithms can help, so you can use computer vision. And actually those algorithms work on your 5-year-old laptop just fine. Yes, you need the SEMs, but you need the data, but then you can work with those algorithms. You don't need a supercomputer to do this. And finally, reverse engineering is a human-computer interaction challenge, and it starts with enabling humans researching hardware, and algorithms are just a part of that. So, with that, I'd like to thank you very much.
Thank you, René. Thank you, E7Ps. Thank you, Stefan. If you would like to ask your questions, please queue up at the microphones. There are 4 of these in the room. And I would say we start with a question from the internet in order to give everyone time to get to the mics. Signal Angel.
Yes, so the first question from the internet. Are the speakers aware of any real-life cases of malicious attacks performed at a logic cell level?
So we are not aware of any actual attacks, so nobody knows if there is any hardware Trojan. We didn't find one yet. So.
But not finding one doesn't mean that none is out there, and also doesn't mean we shouldn't do research in this space.
Thank you. Microphone number 4, your question.
Thanks for the talk. I was wondering if you can do this validation in a black box manner. So when you display the pipeline, how to produce a chip, you mentioned the validation step, which I assume is software based. So why can't you use the same validation, just piping the validation into the chip and avoid all this hassle?
Not quite sure what you mean by piping the validation into the chip. So the validation stage works on verifying that the design file, if you simulate it, works as intended. No?
Yes, and if you couldn't run this validation, but against the chip, isn't this possible?
Yes, so there are validation methods that you can run on the chip, right? But they wouldn't catch every single state of the chip. Maybe the hardware Trojan only triggers after a year or something, and then you would need to test for a year until you find this hardware Trojan by testing. That's the problem.
Thank you. Microphone number 2, your question.
Hello. I have one question. Where do you think is the boundary between just simply uploading software onto the chip and testing it with software and your method that you presented right now? Because I'm asking because I'm working for a chip company, and fun fact, I actually did test if the debugger was off after switching it off.
Yeah, so, well, this was a really contracted example. No? Like, you wouldn't build a Trojan this way because, as you mentioned, like if you do your chip design properly and if you do your validation properly, you would catch this. But it's very possible to build triggers that are way more complex than this. For example, if you flip specific key bits to a certain position, you can't really test that exhaustively. Otherwise, you'd be like brute forcing AES. So if you have this kind of thing, and well, you don't have the gate by gate probing capability, which like for huge chip you probably don't have. If you have such a complex trigger, then I'd assume that with those methods it's a lot harder to find. But yes, this algorithm, this example can certainly be broken with this, yes.
Okay, cool, thanks.
Thank you. Signal Angel, another question from the internet, please.
Yes, next one I have is, are the fabric layers also analyzed to find Trojans implemented by adding, removing, or altering the interconnections of the logic cells?
Very good question. So, of course, you can also build some simple hardware Trojans, I would say, by only going to the routing between, so the interconnections between standard cells. And we have not covered that fully because we only have this single layer, which is the standard cell layer. If we want to cover that as well, we would need to delayer the chip layer by layer, scan every track in the layer, and then some methods for hardware reverse engineering would be employed, and then you can tell the difference.
In the future, we might be able to use synchrotrons to scan the insides, the metal insides of chips, but that's probably still maybe a decade away.
And until then, it's very complex to do that.
Thank you. Microphone number 1, your question.
Yes, thanks for the talk. Are there other possibilities you can think of how a chip could be like manipulated? I'm thinking of like attacking the dotting of the transistors. Is there something else, or what you can think of?
So we are aware of dopant Trojans. I'm not sure.
Yeah, exactly. There's a case study showing how a random number generator could be manipulated by basically making transistors always on or always off on the dopant level. Then it was also claimed, okay, this is not detectable when we're taking scanning electron microscope images. And then a year later, there was an academic paper which actually implemented this. And then they showed, well, if I have a rough idea what I'm looking for, I could also detect those changes in the doping.
Gates that look like different gates, camouflaged gates maybe in this direction.
Yes, there's obfuscation, of course.
So fake bias.
Fake wires, yeah.
So endless opportunities to manipulate chips. Yeah, we need to work on the detection methods.
All right. Thank you so much for a great talk. Thank you for answering the questions.